please don't hesitate in interrupting me and asking anything you want. If I don't have time or enough time, then we can discuss it during the break, but otherwise I will try to answer the question. The more interactive it is, the better it is. Secondly, Himanshu shared with you a couple of documents on the WhatsApp group right now, I think a few minutes before. It contains the handouts of the slides, and more importantly, the lecture notes. The lecture notes is part of a book we are about to finalize. So if you spot any typos, any mistakes, please let us know. Okay? And then this was it. Now I can start. Well, yesterday, Hank talked about the fundamental lemma. That was the main topic. And he showed 3 applications of the fundamental lemma in the context of data-driven control. And what fundamental lemma does is, what fundamental lemma says is that if you choose a particular kind of input, an input which is persistently exciting, then you can, in principle, identify the underlying system generating this data, or even parameterize all trajectories of that system. And that can be used in the context of data-driven control, like Hank showed, for tracking, for, what was it, MPC. But there is a very critical question if one starts data-driven control with the use of fundamental lemma. And the very critical question is, why are we doing that then? Because you can identify the system, and if you identify the system, it's the end of the story. We have a very rich model-based theory. You can apply all sorts of techniques from model-based theory. So what is the benefit of data-driven control if we apply this input, if we are able to identify the system? And this is a kind of ongoing discussion. People have different opinions. But even if there is some benefit, it is going to be marginal. So today what I'm going to do is to escape from the fundamental lemma. And start thinking about what we should do in data-driven control. Okay? For that, we have to forget everything we know about fundamental lemma. And we start thinking from scratch. Now this doesn't work. So let's discuss about model-based versus data-based control. Okay? So in systems and control, we start with a dynamical system to be controlled. This can be any physical system, right? And the first thing we need to do is to come up with a mathematical model of the dynamical system we have. There are alternative ways of obtaining a mathematical model. If we know the physics behind, we can use first principles modeling. We can use Newton's laws, Kirchhoff's laws, whatever physical laws we know to obtain a mathematical model. typically in the form of a differential differencing equation or a transfer matrix or so. But once we have, but there are alternative ways. If we don't know, especially the physics behind the dynamical system we are looking at, we can collect some data, use system identification methods to obtain a mathematical model. And once we have a mathematical model, then we can use this very rich theory of model-based systems and control to do whatever we want to do with this dynamical system. All sorts of performance objectives, all sorts of analysis tools are developed within model-based control. Okay? Now, what I want to do, or what we want to do all together, is to take data in the center of the discussion, but not mathematical model, and create systems and control theory from scratch, but a data-based one rather than a model-based one. So basically, I don't want to deal with mathematical models. I want to work with data only. And I want to alternatively, ideally, do everything I can do here in this world, model-based world, in data-based world. But using data only. Okay? Well, for that, we need to somehow come up with a framework for data-based systems and control. We have to be able to formulate problems and solve problems. And if you don't formulate a problem, it is very difficult to solve it because there is no problem. And that was my difficulty initially in understanding papers about data-driven control. There's some data, but there is no formal definition of a problem. So it's not clear what the problem is. But it is not so in model-based control theory. We formally define problems and then solve them. And let's see how we do that. Well, we typically start with a model class, a class of mathematical models. This can be linear or nonlinear state space models, or transfer matrix models, or maybe autoregressive models, like in behavioral theory. But we have a certain model class. So we start with a certain model class. Then, among this model class, we are given a specific model, the model that corresponds to the dynamical system we are interested in. Let's say S system. And then there are typically two kinds of problems we study. One kind is analysis problems. I want to check whether this system S has a certain property, P. And this can be stability, controllability, stabilizability, just name it. A property one can associate to a system. Right? And the second type of problem is a design problem where we have a certain control objective This system has certain inputs, and we want to shape its behavior by attaching the system as another system, a controller, and to achieve a certain control objective O, let's say. It can be stabilization, optimal control, H infinity, whatever. Right? So this is how we proceed in model-based systems and control. Let's go over it very quickly one more time. We have a certain model class. We have a particular system in this model class. And we have two kinds of problems, either analysis or a design problem. Let's think of a, do I have an example? No, let's think of some very simple example. For instance, imagine that I look at x dot equals ax, autonomous systems. So I am given an A matrix which determines the system I am looking at, and then I want to check stability. First, I formally define stability, and then I study stability, right? Controllability, all these problems. Right? Now, I want to do the same, but based on data rather than model. For that, we need a framework, because I want to precisely formulate the problems I am interested in, and solve those problems. Is this point clear? It is maybe the most, what I'm going to do is maybe the most important point of the entire course. At the conceptual level. Any questions? So how shall we start then? Well, if I don't know anything about database, I just go through model-based and try to mimic it. Let's start in the same way. So I have a certain model class. Again, nonlinear, linear, state space, transfer matrix, AR, whatever you can think of as a model. Within this model class, there is a system, but since I don't know the mathematical model of the system, it is an unknown system. Because I don't have the mathematical model. So within this model class, I have an unknown system. One particular system in this model class. But I don't know this system. Instead, what I can access is some data collected from this unknown system. Input, output data, state, input data, just whatever data you can imagine. All right? So this is the starting point. But I don't want to make any assumptions on the data to begin with, because I want to build a theory. So why should I assume things? I have to figure out. Do we assume, for instance, controllability when we start to teach, in my case, an introduction course to linear systems? No, you first define controllability, right? Since we don't assume anything on the data does not necessarily uniquely determine the underlying system. It may happen that there are many other systems in this model class that can generate the same data, D. It is a little bit unfortunate maybe, but since I gave up the knowledge of mathematical models, I don't have a mathematical model, I have some data, this is the price to pay. Huh? Then we can define the set of systems in this model class which can generate the given data. Let's call it sigma D, a set of data consistent systems. So there is this set now, and any system in this set sigma D can generate the given data. Therefore, by looking at the data, I cannot distinguish any two systems in this sigma D. They are equally likely to be the true unknown system. So what I know only that the unknown system is in this set. The true unknown system is in this set. Now, suppose I want to verify a certain property for that system, like stability, stabilizability, controllability, observability, whatever. The only way I can guarantee that the true unknown system has that property is to make sure that all systems in sigma D have that property. Because then and only then I can for sure know the unknown true system has that property. Let's take a system property P, and we are going to say that the data are informative for the property P if, this is a shorthand notation for if, for definitions, this property holds for all systems in sigma D. If that is the case, then I know that the true system has this property P. If this is not the case, then I cannot say for sure whether the true system has this property. It may or may not. Because the only thing I know about the system is that it belongs to this set. Okay? You see, well, one needs to really give up this system identification kind of thinking. I don't care if I can identify the system or not. As long as I have some data, I have this set of data consistent systems, and I can work with it. It may happen that I can't solve certain problems, but doesn't matter. I do whatever I can do. This is the best I can do. And so this is the definition of informativity at a general high level for an abstract property P. What about a certain control objective? Somebody says, I want to achieve H-infinity performance of, I don't know, 0.2 for this unknown system. Then I can only guarantee such performance control objective if I can find one single controller, C, and whenever I attach this controller to a system in this set, the closed loop system achieves objective O. One single controller for all of them. If that is the case, even if I don't know the true system, I can control it. Huh? Is this clear? This is the data informativity framework. So now, depending on the model class, depending on type of data, also nature of data, whether it's noise-free data or noisy data, depending on different system properties, control objectives, we can study all sorts of data-driven problems within this framework. And this is the framework, because what is the entire starting point of data-driven control? That the fact that I don't know the mathematical model. What do I have instead? Some data. Therefore, inevitably, you are looking at this set of data consistent systems. And if you want to guarantee something about the unknown true system, you have to guarantee it for all systems in this set. There is no escape from it. Okay? Any questions? Yes?
Here, in this framework, we are losing some things, right? There may be a controller for S, but it may not work for all. That is, we are sort of
sure, but yeah, but I understand what you mean, but I don't agree with it. Because when you say we are losing something, it's up to the information you have. With this information I have, this is the best I can do. Of course, it may happen that if I have better data, which makes this set smaller, I can design a controller. But I am trying to come up with a theory which depends on the data. For some data, it is going to be possible. For some other data, it is not going to be possible. And I want to come up with, ultimately, so what I want to do within this framework is ultimately to figure out conditions on data for a given system property or control objective so that data are informative. And ultimately, I want to design an experiment which gives me informative data. We know one instance of experiment design already from Hank's presentation yesterday. If you have a controllable linear system and you have an upper bound on the state space dimension, you can apply a sufficiently persistently exciting input, and the output you collect is going to be informative for system identification. You can uniquely identify the system. That's an experiment. But it's for system identification. Ultimately, my goal, by the way, we don't have any results of that sort yet, but ultimately the goal is first to understand conditions on the data to be informative for a given problem, and then design an experiment to collect informative data. If one can do that, there is no need to deal with mathematical models. It's plug and play. You apply some input, collect some output, and then calculate your controller.
This controller fee depends on the data?
That's a very good question. Indeed, by definition, not, but of course, it's going to depend on the data. So for different data sets, you may get different controllers if the data are informative.
of sigma d
Well, if we know the model class and the data, then we can find out sigma d. We will see soon examples for different types of models, for different types of data, how we can write down the set of sigma d.
We have a system, for example, we have that kind of set which is consistent with the data that we have collected, basis property, and that every system in that set is consistent with each property as well as for observability that we have controller we are designing. So doesn't that make the set essentially to yes? Because each and every model is satisfying the same properties as well as following the same observability.
I couldn't catch the question.
So what I'm saying is that if every system in the data informative set that we have are satisfying the same properties, as well as they have the same controller for the property that we want to analyze, doesn't that make that particular set essentially to be S?
Why? Because there is robust stabilization problem, right? You have a particular system, nominal system, and in a certain neighborhood of that system, you can stabilize all systems with a single controller. One controller can stabilize many systems, right? So the question, as far as I understand, was if the data are informative, doesn't that mean that this set of data consistent systems is a singleton containing the system only? But that's not true. But for some problems, the data may be informative only if you can identify the system. We are going to see examples of it. Yes?
Like you said that data consistent system, sigma d, singleton set. So maybe we can come up with a property class that defines set of properties of all the systems. Then there is one subset of properties which is common for all the systems within the sigma d.
Yeah, but that is what we are going to do.
While designing the controller, we have to consider the properties that are not commonly present for all the systems that are not in the set.
Sure, I agree. But of course, all these depend on certain assumptions we are going to make, starting with a model class, whether the data is noisy or noiseless. All these are going to determine the geometry of sigma d, the set of data consistent systems. And indeed, then, we have to use the property or the objective we are given to analyze under what conditions on data we have informativity. Yes? Yes, we assume that we know the model class. But that is inevitable, of course.
That is also different.
Yeah, in principle, indeed, if you have more data, then it's going to shrink. In principle. It may or it may not. It's also about the quality of the data. Because if I have a certain data set and then I append zeros afterwards, for instance, it doesn't bring any extra information. But in principle, indeed, it should shrink if we have more and more data. Okay? So what is the advantage over system identification or direct or indirect method, let's say? Indirect means first direct, what was it? I got confused. Which one is direct? First system identification? No, indirect. Indirect means first system identification and then designing a controller, right? Well, there is a kind of, I am not a system identification person, but there is a misconception about system identification one needs to clarify. In the noisy data case, it is impossible to uniquely identify the underlying system. You can come up with an approximate system, and very often this approximation is approximation in the sense of distance between matrices rather than input-output behavior. So the quality is under question. So if you have noisy data, indirect method doesn't work anyway. Well, you cannot identify the system. Okay? And although today I'm going to devote the entire day to noiseless data, noisy data is what we are interested in practice. And so indirect method for the noisy case doesn't yield much. And if there is no noise, then as we will see, we do not assume identifiability of the system, but per problem, we will see whether it is required or not. Any other questions? Okay. Yeah. Yeah. Yes. This is in behavioral framework, but there are two things I can say about it. To begin with, the notion of unfalsified models is used in modeling and system identification mainly. And secondly, very often, it is about infinite data. There are also papers which work with some sort of unfalsified models with finite data, but one has to be very careful then, and I am afraid most of them are not that careful because it doesn't exist in general and so on. We can discuss it offline in more detail. Oh, right now, again, one more time before jumping on some examples, we have a known model class, that's something we know, an unknown true system, given data, data consistent systems, and we call the data informative for a property. If that property holds for all systems, for all data consistent systems, and for a control objective, if we can find a single controller that achieves this control objective for all data consistent systems. Okay? Now, let's start with noise-free data and analysis problems. But before looking at concrete problems, I want to say something about exact data, noise-free data. Well, obviously, from practical point of view, it has limited, at the best, limited applicability. At the best. And most likely, no applicability at all. Right? Because the data are not going to be exact. We make measurements. But this shouldn't be a point not to study noise-free case. because, at least personally, I do not know how to study noisy data case without understanding how it works with noiseless data. For me, it is impossible. But it is of course, it's a valid point. Another merit of starting with noise-free data is to see the general fundamental limitations of data-driven control. Because it may happen that we can't do anything with data. And if in the noise-free case I can't do something, definitely with the noisy case I can't do anything. So it's better to understand fundamental limitations. Okay? And something funny about noise-free data. So we started working on this in, somewhere in December 2018. And April or so next year, right? April 19, we submitted the first paper to IEEE transactions on automatic control. And it was accepted in 7 weeks, which is my personal record. It's less than 2 months. Reviewers liked it very much, but they all also had this critical point. It's about noise-free data. But whenever there is such criticism, we have to always come back to this point. If you don't know how to study noise-free data case, how can you study noisy case? Of course, at that point, it was impossible to convince reviewers because we didn't have any results on the noisy case. But I was sure that we are going to have some results. And indeed, later on, we solved all sorts of problems in the presence of noise as well. Conceptual clarity is very important. Sometimes people say, okay, this is not about noisy data, but just hold on. The first thing is to understand, and without understanding, we cannot go further. I'm getting older, so I make all these philosophical mumbo-jumbo comments. Sorry about that. All right, now, and let's start. Let's start from something very, very, very simple. Autonomous systems. Here's this setup. This is the model class I'm going to look at. Just an autonomous system. Of course, all systems in this talk, in this course, are going to be discrete time to make things easier. I have n-dimensional state, this matrix n by n. This is the model class. And among these systems, I have one true system, AS, but it is unknown. Okay? But I collect state data. I measure the state. I forget about practical issues. We are building a theory. We are trying to understand the basics. So I collect states on a horizon from 0 to capital T. Okay? So I don't know the true system. What I know only is this state sequence. Well, if I define X minus as the first capital T columns of this matrix X, and X plus as the last capital T columns, then they are related to each other in this way. X plus is equal to AS times X minus, right? Let's read it. X of 1 is AS times X of 0. X of 2 is AS times X of 1. Huh? Since I collected the data from this system, then this relation has to be satisfied, right? But I don't know whether there are any other systems which can generate this state data. I can define data consistent systems, right? I'm going to drop D, sigma. These are all A's such that XA plus, X plus is equal to A times X minus, which means that given data can be generated by this system with A. Huh? Is this clear? Now, I can ask many questions. To begin with, let's make this observation again. AS is going to be in this set, of course, because I collected the data from this truth unknown system. So now, for instance, I can ask myself, this is, of course, a Mickey Mouse problem. The issue is not about mathematical hardness of the problem or so. It's about at the level of, it's about conceptually how the framework works. So I'm going to call the data informative for system identification if this set of data consistent systems is a singleton and therefore is equal to this singleton set with AS only. Right? Now, it's easy to prove that the data X are informative for system identification if and only if X minus has full row rank. Because A is a solution of this linear equation, and for linear equations we know a couple of things. In this case, this system is consistent. There is at least one solution, AS, and all other solutions are going to be of some specific form and generated by the left annihilators of the matrix X minus. Right? Is this clear? Good. Okay, now, this is, of course, not that interesting. Now, I want to ask myself something about stability, but first I have an observation. If X minus has full row rank, then it must have a right inverse, something like X minus dagger, defined as X minus dagger, X minus dagger is identity. Of course, it is not in general unique, but there are right inverses. Okay? Therefore, if I take any right inverse of X minus and multiply this equation from right by X minus dagger, I see that AS is equal to X plus X minus dagger. And this is true for any X minus dagger, for any right inverse. Right? Okay. Fine. Now, let's look at stability. We are looking at discrete time systems, therefore A is stable if all eigenvalues have magnitude less than 1. They are all in the open unit disk in complex plane. Now I'm going to call the data informative for stability if A is stable for all A in sigma. So this is the data informativity framework. The only way I can guarantee stability of AS is to guarantee that all A's in this set sigma, data consistent systems, are stable. That's the only way. So now, the question is the following. Is it possible that the data are informative for stability, but not informative for system identification? So is it possible at all, without being able to identify the system, I can decide whether the system is stable or not? The answer is no, it is not possible. The data are informative for stability if and only if X minus has full row rank. That was the condition for system identification. And X plus X minus dagger is stable, but this is the AS matrix. So which means that for this particular, very particular setup, without being able to identify the system, I cannot decide whether it is stable or not. And the data should be rich enough to identify the system. That's a turn-off, right? Because it's, we introduced this framework and everything boils down to identifiability, it feels. But it is not so. This is just the beginning. Well, how can I prove it? Well, if part, what we want to prove is if X minus has full row rank and this is stable, this is obvious because if X minus has full row rank, then I know that sigma is a singleton and contains only AS. And I also know that AS is equal to this matrix for any right inverse of X minus. But since this is stable, then I'm done. This is typical, right? If there's an if and only if statement, at least one side is obvious. The other one is more difficult. In this case, it is not so difficult, but we need to write it down. So now only if part. What I want to show is that if the data are informative for stability, which means that all elements of sigma are stable, then these conditions are need to be satisfied. I have to be satisfied. Well, I do the following. So now, what do I want to show is that X minus has full row rank. So I take some Xi such that Xi transpose X minus is 0. If I can prove Xi is 0, then I'm done. How can I prove it? Well, the information I know is that X are informative for stability. So if Xi satisfies this relation, and A is an element of sigma, a data consistent system, then A alpha, defined as A plus alpha Xi transpose, is yet another data consistent system. Because if I look at A alpha times X minus, so A is in sigma, implies X plus is equal to A X minus. I also know C transpose X minus is 0. Therefore, A alpha X minus is equal to A X minus, and that is equal to X plus. X plus is A alpha times X minus. Therefore, A alpha is also a data consistent system. And this is true for any alpha. Okay, so because the data are informative for stability, A alpha must be stable for any alpha. Agree? Then, I use the fact that trace of a matrix is equal to the sum of the eigenvalues. Since it is a stable matrix, sum of the eigenvalues has to be less than the dimension n in absolute, in magnitude. Agree? Now I write the trace of A alpha. It is equal to trace of A plus alpha C transpose C. Because trace of a rank 1 matrix of this form, C transpose, is nothing but C transpose C. Now, this quantity should be less than n for all alpha. If C is not 0, I can take alpha very large, and this is going to be violated. Therefore, this inequality is satisfied only if C is 0. But if C is 0, that means X minus has full row rank. If X minus is full row rank, since AS is equal to X plus X minus dagger, and that has to be stable because I know all data consistent systems are stable. Okay? So for stability, for autonomous systems, it's important to not to forget about the data, the model class. We are looking at autonomous systems with only state data, and if I want to verify stability of the true system, I can do it only if I can identify the system. Without being able to identify, I cannot say whether it is stable or not. Is this clear? Yes? I can't hear. You mean here? All eigenvalues are in the unit disk. They have magnitude less than 1. So if I add if I look at the trace and the magnitude, it has to be less than the dimension of the matrix. Okay? So here is the contrast, system identification and stability, and we clearly see that in this scenario, without being able to identify the system, we cannot decide whether it's stable or not. Okay, now, let's make it a little bit more interesting. Now I want to look at input state systems. This is my model class. X is n-dimensional, U is m-dimensional. And within this model class, we are given a true system, AS, BS matrices, that are unknown. But we are given input and state data. U minus, exactly capital T, input samples, and X, capital T plus 1, state samples. Yes? Is there any relation between N and M? Or?
Capital T, is it related to N or is it related to
No.
M?
I take them completely arbitrary.
So is it to be larger than N or M?
I don't make any assumption at the beginning, but later on, when we study a problem, it may happen that T needs to be greater than N, or maybe even bigger, but we want to see it only after analyzing. At the beginning, I don't make any assumption. That's also a good point. We don't make any assumption on the data whatsoever, not even about the size of the data. Data can be anything, and we want to figure out the conditions on data. And once we figure out, indeed, sometimes, most of the time, we see that T needs to be at least as many as N or even more. Okay? Now, what about data consistent systems? Well, what I know is if I again define X plus as the last T state samples, X minus as the first T state samples, what I know is that this linear equation is satisfied because I collected the data from the true system, ASBS system. Therefore, the set of data consistent systems is given by this set, AB pairs, such that this linear equation is satisfied. And in particular, of course, the true system is within this data consistent system because we collected the data from the true system. All right? As before, I start with system identification. Of course, this is not an interesting system identification problem. I just want to make a case for data informativity. Otherwise, it is not interesting. But let's see under what conditions we can identify the system. Well, if I write this equation in a different way, like X plus is equal to A, B, X minus U minus, X minus U minus and X plus are given. So this is a linear equation. It has a solution, and it has a unique solution if and only if X minus U minus has full row rank. Therefore, I have this theorem. Immediately, the data are informative for system identification if and only if this time X minus U minus matrix has full row rank. And as before, if this matrix has full row rank, then it has a right inverse, and I can find out ASBS from this formula, where dagger can be any right inverse. Okay? Now, and suppose somebody enters this room with some data and asks, could you please verify the unknown system is controllable or not? Huh? I'm going to show that we can, but the question is, do we need identifiability? Huh? So, can I, in other words, can I, on the basis of data, can I decide whether the system is controllable even if the data do not uniquely identify the system? Huh? What do you think now? Okay, let's see. First of all, of course, if X minus U minus has full row rank, there is one single AB. I can find the SPS, and I can check whether this pair is controllable or not. Huh? There is a sufficient condition. But is it necessary? Huh? That's the question. Now, I'm going to say the data U minus X are informative for controllability if all systems in data consistent set are controllable. Okay? And I want to find out now conditions on U minus X so that they are informative for controllability. Well, there are alternative tests for controllability. Henk mentioned already Kalman test, but in the Netherlands we like Hatus test better because Hatus is a Dutch mathematician who is still alive, living in Eindhoven, must be over 80. Well, of course, it is called Popov-Belevich test in some books, but we call it Hatus because he's Dutch. Which says that a pair is controllable if and only if rank of this matrix is full, it has full row rank, for all eigenvalues of A. This is the same as the Kalman test, but sometimes it is easier to use Hatus test. Okay? Now, here's a theorem. U minus X are informative for controllability if and only if X plus minus lambda X minus has full row rank for all complex numbers lambda. Before proving the theorem, I want to stress a couple of points. Number one, this condition resembles a Hatus test with one important difference. Hatus test is about finitely many lambdas, only eigenvalues. But this one has to hold for all complex numbers. That's a major difference. Okay?
Is there a typo there? The rank of that matrix is full row rank matrix.
That's a good point. Rank of this cannot have full row rank. That's a good point. It has to be the matrix. Which slide is it? 16. Okay. This matrix, forget about this rank. This matrix needs to have full row rank. Thank you. That is one point. And the second point, before proving it, by the way, Hank made that joke yesterday that he had good news and bad news. Bad news was there are proofs, and good one was there's only one, right? I have only bad news. There are proofs, but there are multiple of them. But they are short. Before proving this statement, let's look at an example. So now, somebody enters this room, and I know there are two states. I know the mathematical, the model class. It's systems with two states, one input. And this is my data, state data. This is my input data. So now, I write x minus, x plus. First two columns, x minus. The last two columns, x plus. And then I write x plus minus lambda. X minus, it's this matrix. And obviously, the rank of this matrix does not depend on lambda. It is always 2. Which means that, well, this is another typo. I got rid of the theorem numbering because it was full of numbers. So this means the previous theorem. Because of the previous theorem, then the data are informative for controllability. Okay? But if I look at x minus on top of u minus, then I have this matrix, which has 3 rows and 2 columns, and there is no way that it is going to have full row rank. Which means that from the data, I cannot identify the true system. Yet, I know it's controllable. Indeed, if you consider any system of this form for any real numbers a and b, it is a data consistent system. Yes?
Yeah, so when we say informative for controllability, that does not mean it is controllable. This condition is, so previous condition implies that condition.
Sorry, why do you?
So what I mean to say is, so when I say informative for controllability, that does not mean that systems will be controllable.
They are. That's by definition. Because the definition says that I call the data informative for controllability if all data consistent systems are controllable. All of them. Well, so in this specific example, data consistent systems are of this form. A, B are arbitrary. So I cannot identify the true system. Any system of this form could be the true system, but I know it is controllable. Which already, at this point, suggests that starting with persistently exciting inputs and so on, may not be the best idea. Because there are situations in which we can deduce a property of a system without being able to identify it. So why should I aim at identification then? Huh? Okay, you may say, I'm going to prove it, but there is going to be a tea break soon or now? Now, okay, then I say a few words and then we stop. Okay, you may say, of course, yeah, well, who cares about controllability? Huh? I have a colleague who keeps saying that controllability is not important. For me, I mean, I am not religious, but it is like denying the holy entity or so. It's a big sin to say something like that. But one may say, you know, controllability is not an interesting thing because it's an analysis problem. What about design? We are going to come back to that. First, we are going to have the break, and then I'm going to prove this statement. Any questions? Yes.
The same point.
Yes.
I mean, so if this condition is not satisfied, whatever is on
Yeah.
the right hand
Yeah.
side, I mean, we get that it is not informative enough for.
Yeah. Then you are right. Then the true system may be or may not be controllable. But that is the entire point of data informativity framework. Because it also tells you that you cannot conclude on the basis of data. You need to know more. Maybe if you know more, you can embed it and then,
So this RAM function, how one would like to verify? So if I look at this, it's a polynomial matrix of
very, very good question. So the question is, I made already that remark. This rank condition needs to be satisfied for all lambda. And it is in contrast with how to test, which needs to be satisfied only for finitely many. I'm going to come back to it. It's going to be, there's a finite version. But first, I present the infinite version. But thank you for the question.
Excuse me,
Yes.
I may delay the tea by asking this question. This in system identification, we never thought of controllability. We only thought of observability. So then, why it becomes interesting to ask why you are talking about controllability when we are talking about system identification.
But I am not, okay, I talk about system identification, but my goal is not identify the system. My goal is to make this contrast. For certain situations, for certain problems, I do not need to be able to identify the system to solve that problem. Like if I want to decide controllability, I do not need identifiability. That is the point I want to make. Otherwise, I'm not per se interested in identification. Yes.
Is it like you are considering the data of each sensor, like each state separately or in a combination also it will work?
There is a certain setup here. So I start with state data. Later on, we will also work with input-output data, for instance. But that is a lesser concern. The most important thing is this framework, because it allows you to formulate problems and to solve problems. If you have a different type of problem, something like you have input-output data and you want to infer stability or whatever, that's a different problem, needs a different kind of mathematical tools, but still you can formulate the problem in this framework, and once you formulate, you are halfway through anyway. Okay, let's, sorry.
Indirect method that when we are speaking the system
No,
That doesn't guarantee the
no,
truth.
no.
And how we are making the case that my system structure is going to be something.
Because I have some data collected from the system, right? If, well, because I have some data, I know that A and B need to satisfy this equation, right? And from that, I can solve those linear equations, and from that I see that it has to be of this structure. If you solve the linear equations, you are going to obtain exactly this general solution. I don't assume anything on the structure. It's an A-B system. Right?
Data is coming from a certain word class, which you assume.
Sure, sure. But I mean, of course, you need to know something about the data, whether it's input data, output data, otherwise it's never going to work. And most of the time, inputs are known, so you can apply inputs, and then outputs are there, you can measure. Yeah? Yeah, you can identify only this part and B, but not the second column of A. All right? Let's have a break here then.